Look at this room. Writing software used to mean physically wrestling with hardware. Today, we expect to type a prompt and watch production-ready code generate on our screens in milliseconds. The hardware running our code has scaled exponentially, but the human mind's capacity to hold thousands of interacting system states has not. That widening gap is the core of the eternal software crisis. In 1986, software engineer Frederick Brooks published a famous thesis. He argued that there is no silver bullet, no single technological development that will ever guarantee a tenfold improvement in software productivity within a decade. Today, proponents of generative and agentic AI claim we have finally found that bullet. They argue that software no longer needs to be manually architected. It can simply be grown by intelligent agents. To test that claim, we have to look at the philosophical fault line in engineering. Aristotle divided the world into accident and essence. In software, accidental complexity is the tooling, syntax, and boilerplate. Essential complexity is the system's interlocking logic. Modern AI is a near-perfect syntax engine. It rapidly strips away that accidental complexity, leaving only the core. But that geometric core remains perfectly intact. Because AI cannot penetrate the essential logic of a system, it fails at architecting deterministic, tightly hardware-coupled environments like digital signal processing and safety-critical embedded systems. To understand why it fails, we have to look closely at the specific physical constraints of embedded engineering. Large language models are probabilistic. They predict the next likely token in a sequence. But embedded systems are highly nonlinear, requiring a global understanding of how every component interacts simultaneously. Consider the control system of an autonomous vehicle. What starts as a simple state transition model of 5 distinct states rapidly multiplies into a massive, tightly interconnected web of possible conditions. Localized token-by-token generation cannot map this global state space. When the AI attempts to write control logic, it predictably collides with itself, triggering system-level race conditions. This specifically manifests as timing conflicts between interrupt service routines, the functions that preempt normal code execution, and direct memory access transfers, moving data straight to hardware. Compounding this issue is the physical conformity requirement. Software in these environments must conform perfectly to arbitrary, rigid physical hardware. This introduces the datasheet gap. The AI relies on generalized trading data, but your project relies on the highly specific physical reality of a unique microcontroller. This side-by-side comparison shows the real register mount of an STM32 microcontroller next to an AI-generated configuration. The AI's probabilistic output has completely fabricated configuration bits, highlighted here in red. The model hallucinates these registers because it lacks the embodied physical context of the actual circuit board it is supposedly writing instructions for. Generating code with statistically perfect syntax provides zero value if that code is decoupled from the physical reality of the hardware. These limitations become even more severe when we shift our focus to high-performance digital signal processing. DSP engineering hits a strict cycle-accurate barrier. It requires highly specific hardware optimizations, like utilizing single instruction, multiple data processing, or specialized multiply-accumulate units. This code diff illustrates the gap. On the left is naive, high-level C code generated by an AI. On the right is the hand-tuned, hardware-aware assembly actually required to execute the same logic efficiently on the chip. The AI acts as a mathematical novice. It correctly processes the underlying algorithm, but it is completely blind to the machine architecture required to execute that math safely. This blindness creates what engineers call the temporal void. An AI has absolutely zero conceptual awareness of execution time within a real-time operating system. For example, an AI will confidently schedule a heavy block of floating-point mathematics directly inside an interrupt service routine. Because an interrupt halts all other operations, placing heavy math there predictably violates strict 10-microsecond real-time execution deadlines, causing the entire system to panic and crash. Beyond timing failures, this architectural blindness introduces a secondary threat, documented in the RunSafe 2025 report. the automated scaling of security vulnerabilities. This security heat map of a firmware block diagram demonstrates how a single localized AI error, specifically a use after free memory bug, duplicates and rapidly spreads across hundreds of interconnected functions. In high-stakes environments, the AI's lack of architectural awareness transforms isolated, novice-level syntax mistakes into systemic, cycle-breaking catastrophes. The software industry has proposed a solution to these limitations, deploying multi-agent systems where AIs operate in specialized roles, like coder, reviewer, and architect. This relies on the premise of scalable agency, the belief that running multiple AI agents in parallel will exponentially compress development timelines. The data tells a very different story. We can look directly at the empirical results from the 2025 Cooper-Bench study conducted by Stanford and SAP. The study revealed a highly counterintuitive finding. Multi-agent setups actually yield a 30 to 50% lower success rate than utilizing just a single AI agent. This chart visualizes what we can call Brooks' Law 2.0. As the number of agents on the x-axis increases, the development time on the y-axis shoots upward, driven by an exponential curve, where coordination overhead scales with the square of the number of agents. This data table from the Cooper-Bench report breaks down exactly how these multi-agent environments fail. The two largest issues are modeling partner behavior at 42% and communication breakdowns at 26%. Modeling partner behavior failures occur when AI agents misinterpret the operational context and the intent behind the code generated by their automated counterparts. Communication breakdowns happen when these agents silently overwrite, erase, or contradict each other's commits, completely failing to flag logical errors to the human operator overseeing them. This rapid, uncoordinated churn results in a state of conceptual entropy. Continuous AI-driven refactoring progressively degrades the architectural integrity of long-lived embedded systems. High-speed code manipulation destroys long-term maintainability because the AI fails to record the historical why, the tacit reasoning behind critical design decisions. Adding specialized AI agents to a project does not divide the labor linearly. It multiplies coordination friction and system entropy exponentially. These localized code failures scale up into massive regulatory roadblocks for strict industries like avionics and automotive engineering. At the 2025 International Conference on Software Engineering, pioneer David Parnas laid out a strict framework defining the threshold for software trust. Parnas pointed out that generative AI is stochastic or probabilistic by design. That makes it mathematically untrustworthy for systems requiring absolute, predictable determinism. This creates a major hurdle known as the traceability challenge, which is mandated by rigorous safety standards, DO 178C in aviation and ISO 26262 in automotive engineering. This DO 178C certification traceability matrix shows the required chain of verification. With an AI involved, the intermediate design and architecture links are completely broken, marked here with failing indicators that disconnect the root system requirements from the final generated code. The AI simply skips or hallucinates the intermediate engineering rationale, and that makes legal and safety certification practically impossible. This forces the human engineer into a new role. Instead of producing syntax, their primary responsibility moves entirely toward rigorous system verification. The ultimate, irreplaceable safeguard is human tacit knowledge, that instinctual, senior-level intuition that recognizes architectural drift and signal integrity failures, even when the code compiles flawlessly. True conceptual integrity must originate from a single, temporally aware mind. Software engineering remains an inherently human endeavor. 40 years after Frederick Brooks wrote his thesis, there is still no silver bullet.